Hi everyone, today I'm going to do a quick little demonstration, not a proof, of the derivative of sine x and the derivative of the function y equals cosine x. So let's start first with sine x. Now at the first attempt at this, you probably would default to using first principles derivatives, at least a mathematician would do this, and so the limit as h approaches 0 of f of x plus h minus f of x all divided by h. So I've set this up here where our function is the sine function. So to continue here, I would need the sine of x plus h, subtract the sine of x divided by h. That's nice. Now, here's the thing. If we don't have higher levels of mathematics, we're going to get a bit stuck at this point knowing exactly what to do with the sine of something like x plus h. Rest assured, mathematicians do know what to do with this, and they have figured this out. But we're going to sit there and we're going to go, well, we'll find an alternative way of thinking about this, a technological way of thinking about this, because I'm not attempting to do a proof here. I just want to give a convincing demonstration. So let's start by looking at this quotient, this ratio here. I can certainly have something like this on my calculator with sine of x, but it's the h business. So what I'll do on my calculator is I will store a very small number, like 0.01, in the variable or the memory h. So I access that with the alpha key here. Now h is a number. That's great. I'll also double check with the setup menu that my angles are measured in radians. That's good, like that. And now I'm going to go to my graphing app. I've already put in here the function y equals the sine of x. And I'll draw that. There it is, lovely sine graph from negative 2 pi up to 2 pi. Actually a bit more than that. That's 2 pi there. So that's up to 3 pi, negative 3 pi up to 3 pi. So that's lovely. Now let's just pop back for a minute to here. And I'm going to enter this expression as my second plot. I can't put limit on the calculator, but it's going to therefore be an approximate derivative. So I want the sine of x plus h. Remember, I pre-stored the value of h. Sine of x divided by h. Where are you, h? There you are. And let's draw this. The red graph represents the derivative. Now what does that remind you of? Well, let's just do something else for a moment. Let's sketch the tangent, and this is my first function. The tangent at this point, the origin of my original sine function, it's this lovely green line with a gradient of 1. Look at the value of the derivative function here. It's a value 1. If I move a little bit to the right, you can see that the tangent is the slope is decreasing, and if I couldn't get to the top, that's annoying. But if you could imagine I was at the very top of the crest there, the green tangent line would be horizontal, and the value of the derivative function there is 0. The green line is now a negative gradient, and that's it. Exactly at this point here, it's a gradient -1, and the red derivative function has a value -1. Now what does that red function remind you of? Well, I hope you said it reminded you of the function cosine of x. I'm going to graph these three. There's the sine function, the red one was my ratio, and the green one, which is the cosine of x, exactly overlaps. So, not a proof. Please don't quote me and say that I've proved anything here. A demonstration without proof that the first principle's derivative of sine x exactly coincides with cosine of x. And I hope that's a somewhat convincing argument for you. Now, I'm going to be a little bit quicker over here, and we're just going to edit our way into making this the derivative of cosine. Our first principles rule would be the same. We of course would need to have cosine of x plus h minus the cosine of x, and I certainly wouldn't expect that to be the result, so we'll leave that for a moment until we do something on the calculator and have a look. Let's pop back to there. I'll delete that one. I don't expect that to be the answer. I'll change this one to read the cosine of x. I will edit this one for the same reasons. And let's draw them. Now the blue graph this time is the cosine function. Starts at +1 and one full cycle gets back to +1. Look at the red graph. If I let's put that tangent line back in there. Now the tangent line here is exactly horizontal. The derivative value is 0, as it shows here on the red line. As we move down, we get to a gradient pretty close to -1. That's the lowest point on the derivative function. Gradient is still negative, but increasing to 0. So that's that point there. And I hope you can see that the red graph starts at the origin, but it goes downwards instead of upwards. It's sort of doing the opposite of what a sine graph would do. A sine graph would start here and go upwards. So we've got a function that is a negative sine graph. Oops. I don't need to have that twice. There you have it. Not a proof, but a quick demonstration, I hope, that shows you that the fundamental rule y equals sine of x gives derivative cosine x, and if y equals cosine x, the derivative is negative sine x, actually does stand to reason. For a more thorough proof, consult any serious calculus textbook that you might have lying around on your shelf.